Hello aviators, how are you today? My name is Magnar Nordahl and I'm a retired airline captain. Over the past year, AI has become incredibly capable of generating both text and voice impersonations. As a result, platforms like YouTube has now flooded with a mass-produced AI content. And it's a trend that's hard to escape. Many people don't even realize that the voices they are hearing are artificial. To counter this, genuine content creators are increasingly appearing on the camera to show that their work is authentic. There's another trend, however, that I find even more frustrating. I'm active on LinkedIn, a networking platform for professionals. Most of my connections are in aviation, and they shared valuable insights that I truly appreciate. But some users rely on AI to generate technical content and then post it as their own. While the text might be reasonably accurate, the illustration often falls far short. For example, when I asked ChatGPT to generate an image of a cabin attendant serving the flight crew inside an airliner cockpit, this was the result. Although the people appear realistic, their placement within the cockpit is not. And when I asked for a cutaway drawing of an ATR-72, it ended up being far from reality. Yes, it may look like a real aircraft, but when you start looking closely, you understand something is not right. Just look at the cockpit. It is full of stuff. This should be the cargo compartment. The cabin has 3 seats abreast, but no aisle, no doors. This should be the lavatory and a cargo compartment. Instead, every open space is filled with stuff. So in this video, I'll be taking a critical look at AI-generated illustrations that really shouldn't be shared by serious aviation enthusiasts or professionals. First out, how many labels are wrong? It depends how picky you are. The red arrow, for example, is pointing at the vertical stabilizer, and the vertical stabilizer arrow is pointing at the gap between the stabilizer and the rudder. The ailerons and elevators are far from reality. And the cockpit is not in the cabin. The ailerons must not be mixed with the flaps. And the engine? Next, please. The 4 forces of flight. Drag is correct, and lift is mostly correct, at least until the last line. When lift differs from the weight, the result is acceleration, which we experience as g-force. For example, in a turn, the wings must generate additional lift to maintain altitude. Thrust, fair enough. Although this may sound like nitpicking, thrust is a force, whereas power describes the rate of which the engine produces energy. The statement about left-turning tendency is only valid for propeller-driven aircraft with a clockwise rotating propeller, view from behind. I have flown aircraft with the opposite rotation, which tend to yaw right with increased power. Jet aircraft, on the other hand, do not exhibit this tendency. Weight caused by gravity? That is absolutely correct. Weight is the force exerted by gravity on a mass. For example, if you are standing on the moon, your weight would be about 1/6 of that it is on Earth. Forces in a turn? This is completely incorrect. The correct diagram is very different. Types of turns, skidding turn, slipping turn. Honestly, help. And it only gets worse. Why compare curves of total drag and power required? They are not directly comparable. Drag is a force, while power is the rate of energy production. At this point, everything is just a mess. I give up. ILS stands for Instrument Landing System. It is used for precision approaches and is especially valuable in poor visibility conditions. Where to begin? As the text correctly states, the localizer should be aligned with the runway centerline, but in this illustration, it is shown perpendicular to it. The outer midline inner markers are also depicted, but these are now largely obsolete, having been replaced by DME, distance measuring equipment. And as for the marker beacon antenna, this is what it actually looks like. No, it certainly doesn't have bright lights on top. Distance DME? That doesn't really mean anything, and the labels shown here are incorrect. This is how they should actually appear. And the ILS indicator in the illustration? Honestly, I've never seen anything like it. Here are examples of real ILS indicators, ranging from older instruments to modern glass cockpit displays. Then we have this table showing different wind types, with 3 columns representing the phases of flight: takeoff, cruise, and landing. Starting with a headwind, yes, it reduces the required takeoff distance. During cruise, a headwind increases flight time and therefore fuel consumption. On landing, a headwind lowers the ground speed, resulting in a shorter landing distance. That part is straightforward. For a tailwind, takeoff distance increases, which is correct. In cruise, a tailwind reduces flight time and fuel burn. On landing, however, the ground speed is higher, leading to a longer landing distance. And yes, there is a tiny risk of overshooting if not properly managed. Finally, crosswind. The mention of lateral drag during takeoff and landing is technically true when airflow approaches from the side. It creates additional drag. However, once airborne, the aircraft is flown in coordinated flight, eliminated any lateral drag. During approach, the aircraft is typically flown with a crab angle, remaining coordinated until the flare, where decrabbing induces a brief period of lateral drag. Lateral drag has minimum impact on aircraft performance. As for turbulence in crosswind conditions, well, that's a misunderstanding. The direction of the wind relative to the aircraft does not by itself create turbulence. It's not as if flying in a smooth tailwind suddenly becomes turbulent just because you change your heading 90 degrees. And finally, an airspeed indicator like nothing I've ever seen. Where do you begin? An airspeed indicator is supposed to display speed as a number. Whether it's in knots, miles per hour, or kilometers per hour doesn't really matter. But when the aircraft manual specified speeds as exact values, it's pretty important to know what your actual speed is relative to those limitations. Here is what a proper airspeed indicator looks like in a light aircraft. See the difference? The white arc defines the flap operating range. The lower limit is the stall speed in landing configuration at the maximum weight, VSO. And the upper limit is the maximum flap extended speed, VFE. The green arc represents the normal operating range. Its lower limit is the stall speed with flaps retracted, VS. And the upper limit is maximum structural cruising speed, VNO. Above that is the yellow arc, which extends up to never exceed speed, VNE, marked by a red line. The yellow arc is a caution range. Use it only in smooth air. Now, looking at the flawed illustration, we suddenly get some creative additions. Vx is the speed for maximum angular climb. It depends on the weight of the aircraft and is not marked on the airspeed indicator. Vy is the speed for maximum rate of climb. Like Vx, it depends on the weight of the aircraft and is not marked on the airspeed indicator. Fe is not an airspeed, but a chemical symbol for iron. Then there is Vmc, which you will only find on light twin-engine aircraft, but it's not marked on the airspeed indicator at all. And finally, Va, the maneuvering speed. This is the maximum speed at which full abrupt control inputs can be made without overstressing the aircraft. It's an important speed, but it's not marked on the airspeed indicator at all. Folks, AI is a powerful tool and can be used effectively in many areas. But when it comes to technical illustrations, it still doesn't get it. Maybe that will change in the future. For now, if you want to impress your audience with aviation content, make sure you fully understand the subject yourself. Posting images like this is simply embarrassing and can undermine your credibility. And as always, a big thank you to the supporters of this channel. You make this content possible. Thank you for watching, have a wonderful day, and happy landing in headwind.